So good evening, everyone, and welcome to this lecture. This is lecture number 18. Oh, we are still wandering somewhere between electric field and electric potential. In the previous class, we had seen how we can find out the electric field from electric potential. We had seen that negative gradient function. We know how to find it out. We had also seen the concept of equipotential surface. Yes or no? Do we remember the concept of equipotential surface? And then I told you that with this concept of equipotential surface, if everything is correct, we should be able to find out the electric field as well. And then I told you that we will be solving a question where we would be able to find out the electric field looking at the equipotential surface. These are the three equipotential surface and the distance between them is given. Now the question passes on to you. What is the electric field? You have to find out the value of electric field and you have 2 minutes to do this. So how are we going to do this? The first thing that we can understand is we can find out what would be the direction of electric field. Remember, electric field is a vector quantity, but we are trying to understand that vector quantity from scalar things. Potential is a scalar thing, and equipotential surface, the values are also scalar. We are trying to understand a vector from a scalar, and that's the importance of this. Can anyone tell me what would be the direction of electric field looking at the diagram that I have drawn? And what we know about electric field and potential, and what will be the direction of electric field here? Tell me fast. What would be the direction of electric field?
Along negative x-axis.
Along negative x-axis, and it would be perpendicular to these surfaces. Yes or no?
Yes, sir.
Yes,
What
sir.
type of electric field will it be? Will it be uniform or will it be non-uniform?
Uniform.
It's a uniform electric field. Yes or no?
Yes, sir.
That's it. So we know the direction of electric field. See, there is no vector drawn, but we know the direction of electric field. That is the power of equipotential surface, and that is the power of potential. Scalar quantity, but the scalar quantity is giving us the vector. Now we know between any two equipotential surface, the potential difference is how much? What is the potential difference between this one and this one?
2v.
What is the distance between this one and this one?
5.
And E is minus dV by dr. Remember? It goes from higher potential to lower potential. You know the direction, you know the potential difference, you know the distance between the two equipotential surface. You can get the value of E. What is the value of E? 2 by 5 volt per meter. Do we understand this?
Sir.
How I have got this? Just by using scalar things, seeing the equipotential surface, I found out the electric field, which is in itself a vector quantity. Everyone understands how I have done this? Yes or no?
Yes, sir.
Okay, I'll give you a minute to note this down while I prepare the next question for you. And I hope since we have done this one, you would be able to do the next one. Everyone has noted this down?
Yes, sir.
Everyone has understood the concept? Yes or no?
Yes, sir.
Then comes this one. Some equipotential surfaces are shown in the figure. What is the magnitude and direction of electric field? This question has come, a similar question has come in one of the previous JEEs. And this is a very favorite question because it's a conceptual one. Question number 2 or 1, whatever you call it. What is the magnitude and the direction of electric field? You have 2 minutes to think about this question and get me the answer. So, how are we supposed to do this? Anyone can help me out. I am also thinking what I'm going to do. Can anyone help me out? How are we going to solve this? How are the electric field going to go? From higher potential to lower potential. So they are going to go like this. Yes or no? Yes or no? And they are going to be perpendicular like this. So now I can find out the angle with the x-axis. 60 degrees definitely not the angle because it is obtuse angle. So option B cannot be true in any case. So angle has to be how much? 120 degrees, yes or no?
Yes, sir.
So only two people remain in contention, A and C. It's a final between A and C. Now we have to find out the magnitude. Now do you find out the magnitude? You find out the difference between these two. This is 10 volt, this is 20 volt, this is 30. So the difference is how much? 10 volt. 10 volt is the difference. Then you find out the distance between the two. And the distance between the two is also 10 centimeters, so 0.1 meters. So difference in voltage is 10 divided by 0.1 and the winner is option A. So that is the answer. How many of you got this? Option A? See, everyone. Option A wins democratically. But remember, democracy does not win in physics. Physics does not follow constitution. Physics only follows physical law, and this answer is absolutely wrong. So democracy cannot make it win. The correct answer, my dear friends, is option C. 200 volt per meter, making an angle of 120 degrees with the x-axis. Now comes the question, why and how? Why and how? Why and how? Why and how? Why and how?
We should calculate perpendicular distance between
We should calculate perpendicular distance. That is what I wanted to show you. Here it was the perpendicular distance between the two equipotential surface that I had found out. To find out the perpendicular distance. And that distance was not the perpendicular distance, my dear friends. And that is why your answer was not 10 divided by 0.1. Your answer could not be 10 divided by 0.1. If I just show you an enlarged view of that thing, it has become so big that it has become distorted. This is how electric field lines are going. And you have to find out this distance, this one, the perpendicular distance. This red line, you have to find out the length of this red line. And you can do it by pure geometry. The hypotenuse is 10. The angle is 30. And that line would be you can find out, yes or no? It would be 10 sine 30.05. And therefore the answer becomes 200 and the answer does not become 100. Do we understand this? It has gone above our head saying bye bye. So nikal gaya.
Understood, sir.
Understood, sir.
Okay. Well done. So this is how you can find out electric field, which, my dear friends, is a vector quantity from things which are purely scalar. That is the beauty of this method. So remember this. I was having one more question, but I don't know where that question has gone. So that question has gone somewhere else. I think the question was exactly same, I think. Exactly same. Remember, so you understand the concept, yes or no? There is no point of doing a same question. Now, we understood the concept. Now, what I'm going to tell you are small pointers, small formulae, small concepts, and you can expect one or two questions from those concepts. Okay. So just note them down as important points or whatever. These are small things that may make a lot of difference in your eventual answer. The first pointer is electric field at a point on the edge of a disk. Again, I have seen this question may come, may not come. I don't know. They might ask you as what all factor it depends on. They might also ask you the formula. What is the potential at the edge of a disk? There is no point of me deriving it and just showing how much I know, how much I can derive it. That is not the point. The point for you is to find out what is the answer. So what you have is a disk, and this is a disk, and we are talking about a point on the edge of the disk. What is the potential of any point on the edge of the disk? Remember, potential at infinity is taken as 0. Remember this as important points. Small formulae, small things I'm going to give you. Everything noted down as small points. Remember them, because if a question comes, you don't have to derive it, just write the answer. Potential at the edge of the disk is given by this sigma r by pi epsilon naught. What is sigma? What is r? What is pi? You know this. Sigma is the what? Sigma is what? Huh?
Surface charge density.
Surface charge density. Sigma is the surface charge density. R is the radius of this gentleman. And pi is our pi ka hisab wala pi. And epsilon naught is our old friend epsilon naught. You all understand this? Note this down. Where was that? Okay, this is dipole. Dipole we will do afterwards. No point of doing it now. Let me move ahead. Noted it down, bacha?
Done, sir.
Okay. The next pointer is
1 minute. We are writing. Completed, sir.
things are going to take a turn because this thing got stopped. So it has to come again. Okay. So the next heading is this. Self energy. Now, what do you mean by this self energy? Now, this self energy, remember we have talked about potential energy of 2 point charges. When we brought first point charge from infinity, placed it here, no work was done. Then we brought the second point charge, but work was done. I told you this energy is known as interaction energy or mutual energy. Do we remember that? Yes or no? Eh? We remember that?
Yes, sir.
Now
Yes, sir.
remember, it was a system of point charge. Now, if you have a conducting sphere, or a conducting or a non-conducting shell, in all these three cases, the charge will come on the outer surface of the shell. Do we understand this?
Yes, sir.
Now, to put the charge on the outer surface of the shell, all these point charges will have to be brought from infinity and put on the surface of the shell. Do we understand this? Because of this work done, energy will be stored in this conducting sphere or a conducting or a non-conducting shell. That energy is known as the self energy. And remember, this self energy is always positive. We have seen that the mutual energy, interaction energy, if one is positive and the other one is negative, the interaction energy becomes negative. But self energy is always positive. Remember this. Self energy of anything, whether it is a positively charged sphere or a negative charged sphere, self energy is always positive, and the value of this self energy of this sphere, anyone knows it? Anyone knows it? It is kq square by 2r or you can now remember it as q square by 8 pi epsilon naught r. From now onwards, we are moving on to the next chapter. Capacitance will not be using K now because K is dielectric constant there. So we will use it as 4 pi epsilon naught. This is the self energy of a conducting sphere or a conducting or a non-conducting shell where charge is only on the outer surface of the shell. Do we understand this? Yes or no?
Yes, sir.
Then we have one more type of body which is left. What is the next body which is left? Which we might not use it, but you have to know the formula. So the next heading would be self energy of a non-conducting sphere. Now, when the sphere is non-conducting, have you noted down the first formula?
Yes, sir.
Yes, sir.
Everyone?
Yes, sir.
Okay. So, then we come to this formula. This is the self energy of a non-conducting sphere. When it is a non-conducting sphere, charge is inside the sphere L as well as on the surface of the sphere, and therefore the energy becomes different. You must remember the formula of energy for this. The way I remember it is 3 by 5 k q square by r. Again, it is always positive. That is the self energy of a non-conducting sphere. You can put k as 1 by 4 pi epsilon naught. So I think, and this is the form that it gets, 3 by 20 pi epsilon naught r multiplied by q square. Do we understand what we are writing here? What is going above what it's saying? Bye bye, bye bye, bye bye. Have you noted it down, bacha?
Completed, sir.
Then we might have a question like this where this would be required. This would also be required. Chapter on gravitation, probably. This two non-conducting, hollow, uniformly charged spheres. So it is hollow, non-conducting sphere of radii r1 and r2 are given charges q1 and q2. Placed at a distance of small r. Find out the total energy of the system. You have 2 minutes to show me your talents. Question number 3. 2 minutes you have. So how are we supposed to do this? Anyone? Everyone was sleeping or what? I have to find out the total energy of this system. How will I find the total energy of this system? I will find the energy of body 1. I will find the energy of body 2. And then I will find the interaction energy of body 1 and body 2. Am I audible, visible? I am there in the, we are in the same universe, no?
Yes, sir.
Or you have slipped in some other dimension? Same dimension, no?
Yes, sir.
Okay, great. What is the energy of the first sphere? Tell me. Huh? Q1 square by 8 pi epsilon naught R1. Do we understand this? Do we understand this? Just now we have
Yes,
written the
sir.
formula. Huh?
Yes, sir.
Thank God. What is the energy of the second sphere? Tell me fast.
Q2 square by 8 pi epsilon naught R2.
Why taking so much of time? You don't do anything unless until you are scolded. Yes. What is the mutual energy of the two? Remember one question I had given you. I had asked you to find out the mutual energy. Yes. What is the mutual energy?
1 Q2 by 4 epsilon naught R. Small r.
So why it was taking so much of time? That is the answer. And remember, you may get a question of this nature. I've seen question of this nature of spheres coming and they ask you the energy. If you forget the self energy, that question is gone. Everyone understands this? Yes or no?
Yes, sir. Yes, sir.
Okay, I have one more, I think, on this category. So remember, the number of questions are very limited. And there are some other questions, but they are just too old to come and too difficult to solve in the present scenario. So I will just leave it away. I'll just give you these two ones, because I think out of these two ones, if you are lucky, you may have one question landing up in one of your sessions or one of your papers. So this is the next one. Again, find out the interaction energy of these two. So now I put one shell over the other shell. Two concentric spherical shell of radius r1 and r2 have uniformly distributed charge q1 and q2. Find out the total energy of the system. How you want to find out? Just remember this. Do not make a stupid mistake in the answer, because the options that we be given would be very confusing. 2 minutes you have. So how do I go about doing it? The first one is the self energy of the first sphere. Everyone knows the self energy of the first sphere. Yes or no?
Yes, sir.
This will be U1, that will be equal to Q1 square by 8 pi epsilon naught R1. The second one is the energy of this one. U2 will be equal to Q2 square by 8 pi epsilon naught R2. The third one is the potential energy of these two things. Now, when they were apart, there was not a problem. When they are one over the other, again, there is not a problem. You can find the potential created by this sphere on the surface of this one, or you can do the reverse. Whatever you do, the answer will be same. If you find the potential created by the first sphere on the second sphere, it will be Q1 by 4 pi epsilon naught into R2. If you find the potential created by the second sphere on the first sphere, it will be Q2 by 4 pi epsilon naught R2. You have to multiply it by Q1 and Q2 in the second case or the first case. In any case, the interaction energy will come as Q1 Q2 by 4 pi epsilon naught R2. This is the factor that you have to remember. Do we understand this?
Yes,
Everyone
sir.
got this?
Sir.
Okay. That is, remember, this is how you find out the interaction energies of two bodies. The next heading that we are going to write is known as energy density. Now, this question comes in various forms. This question comes in various forms. It may come as a question in electrostatics. It may come as a question in dimension analysis. What is energy density? Wherever you hear the term density, it is something per unit length or per unit area or per unit volume. Energy density is energy per unit. What? This is energy per unit volume. Energy per unit volume. So you write it like this: du by dv. Small volume dv. How much energy is stored in that small volume dv is du is half epsilon naught E square. That is known as energy density. Do you understand this? That means wherever in space you have electric field, right now I'm sitting in a space which has gravitational field. The same concept can be applied here. Wherever in space you have gravitational field, you have energy stored in that space. How much energy is there in a unit volume? Half epsilon naught E square. You understand this? Yes or no? Now remember the dimensions. I mean, this question comes as a question on dimension. They will ask you the dimension of half epsilon naught E square. Remember, it is energy per unit volume. So from that energy per unit volume, you can find out, you can find out the dimension of half epsilon naught E square. Do we understand this, or this has gone above our head saying bye bye, sir? Bye bye. I'm going, don't worry about me. You understand this? Huh? You understand this? Everyone has noted this down?
Yes, sir.
Then, sir, this, sir, small question, sir, for you, sir. Right from the heart, sir. Please solve it, sir. You will have 2 minutes to solve it, sir. Question number, whatever it is. I've forgotten the number. I'll call it 5. Find out the energy stored in an imaginary cubical volume of side A in front of an infinitely large conducting sheet of volume density sigma. Of uniform charge density sigma, my dear friends. You have 2 minutes to show your talents. So I have answers here, and the answer is, how will you find it out? See, you just have to do simple things. du by dv is half epsilon naught E square. Du by dv energy density. Now I can write du as half epsilon naught E square multiplied by dv. The infinite sheet is the only type of charge distribution that produces uniform field. The field is uniform. So to find out the total energy, you just have to find out the integral of this. That's it, my dear friends. Integral of dv is volume. So the total energy stored will be half epsilon naught. What is the field produced by a sheet? Sigma by 2 epsilon naught. So sigma square by 4 epsilon naught square into AQ. You multiply and divide correctly and you end up with the correct result. Do we understand this? How many of you got this one correct? So many? Well done then. That means you have understood the concept. I just was just looking for what? Looking for if I can see, if I can get that question, I will show it to you, and that would no, not here. Must be here. It must be here. Okay. If I find that question here, I will show it to you, and then you can do the dissection of that question. It must be here in capacitor of energy density. Okay, just looking for that question. If I can find it, voila. If I can't, well, then my memory does not serve me right. Sometimes it does serve me right, sometimes it may not serve me right. In this case, it seems that in this case, it seems like it has given me a gotcha. Just wait for a minute. Where it can be. Must be here then. It's not here. Then it must be here. No, it's not here as well. Okay, so what I'll do is I will find it out and I will do it in the next class. I'm just not able to find out. My memory has dished me. It should not have dished. And normally remember the question if I see one, but this time around I'm not able to find out the question that I was looking for. I mean, that question would have served as a good parting question for this particular case. I'm just not able to locate that question. Must be here, but not able to locate it. Just not able to find it out. So I will find it out and probably we'll do it in the okay, that was the question. So I got it at last. This was the question taken from one of your favorite books, your CV, and this was the question. This is question number 43 on page number 168, and this is exactly same as the question that we did. So this is the only question here. So I hope you can do this question. Then there is question number 41 and there is question number 42 as well. Page number 168. You can solve those questions on your own. I think I have told you enough that you can do those questions on your own. So try them. And this is the one that we have already done. We already know the answer for this one. So on that note, we will end this class. Take care. And I'll see you in the next class tomorrow. Bye bye. If you have any doubts, you can always come up to me. God bless you all.
Bye, sir.
Bye.